Welcome back. Before we actually move to discussing the effect of substituents, I do like to take the time to point out one special case of Friedel-Crafts alkylation. Remember where we talked about benzene reacting with CH3Cl and AlCl3, right? Now, when it is CH3 or CH3CH2, there's no problem, you know? It would work exactly the same way. You would make only one type of product like I showed you, but when you have that extra CH3, CH2, CH2Cl reacting with AlCl3, there is something called a hydride shift that happens, okay? What that is this essentially leads to tying up the idea of tertiary, secondary, and primary carbocations that we learned in the previous case. Now, if you remember, when we learned the CH3Cl AlCl3, we produced CH3 plus AlCl4 minus, right? Now, this is a carbocation, okay? This is, this is the least stable carbocation, right? Now, keep in mind, we have tertiary carbocation, which is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl carbocation, right? This is a methyl carbocation. It's a carbon attached to 3 bonds, all 3 are hydrogens, whereas a tertiary is a carbon attached to 3 bonds, neither of them are hydrogens, and you have a positive charge, right? So you may not always have to make tertiary, but if you can make a secondary instead of a primary, or a primary instead of a methyl, then that would lead to a more stable product. Now, say if this were the 2 reactants, then the electrophile resulting from this would be, as I said, you simply put the plus charge on the carbon containing the alkyl group plus AlCl4 minus. This is going to be constant. Now, this is a primary carbocation, right? Carbon containing 2 hydrogens and a positive charge. Now, cool thing is, this would react as it is with your benzene ring. So this what is going to react to with this, establish the link. So in the process, you're going to make right. Keep in mind, you always have this hydrogen, and then you have a hydrogen here, and the positive charge is here now, right? And then the AlCl4 minus, which is the base, comes and grabs this hydrogen. This bond comes in, leads to the formation of this. This is actually one of the product. It is a minor product. Okay. Then what is the major product? Okay. The major product is, I'm going to draw this all in a different color so it makes more sense to you. Okay. So you have, I am going to write, okay, the CH hydrogen as, like we used to draw the full skeletal structure, and this is the plus charge, right? This is the same as the one above. This is a primary carbocation because this carbon contains 2 hydrogens and a positive charge. But what if we can move a hydrogen from one of the neighboring carbons into this carbon that currently contains the positive charge? Therefore, we can move the positive charge into a different position. So that means what I'm going to do is move this bond, this with the hydrogen here, and move the positive charge over here. What does that do? Well, basically, you've lost a hydrogen, but you have now obtained the positive charge on the middle carbon, and the hydrogen has now gone here. This is an isomer of this. Remember how in 330 I made you write different isomers for, given a positive charge? It's exactly the same thing that's coming back. But this time it's in the context of a reaction, so it makes more sense. Now, this is a primary carbocation. This is a secondary carbocation. You cannot have a tertiary for this one, okay? Because I could show you later down the road, through a homework or quiz, that I can have you generate a tertiary carbocation. But because of this hydride shift, that all we have done is move the hydrogen here, and in turns we move the positive charge onto the carbon that from which we are moving the hydrogen. So now we have a secondary carbocation. A secondary carbocation is more stable than a primary carbocation. So this, when it reacts with the benzene, okay, I'm going to make this font a little smaller so I can fit all of this in this page, right? So this bond now reacts with this carbon, leads to, again, you want to make sure you don't attach random things. You can write it this way, modify it, but make sure that this bond connects to this carbon containing the positive charge. And then your positive charge is here now. Remember, we have hydrogens here. So your base, which is your AlCl4 minus, comes and grabs this hydrogen. So this bond comes over here, which leads to the formation of, it looks kind of the same, right? But it's so much different. The procedure is the same, but the products themselves look different. This is a minor product, and this is a major product. So this type of shift only happens when you have 3 or more carbons, minimum. You cannot do this with the Friedel-Crafts alkylation. You must have a minimum of 3 carbons. You see, in this case, we have 3 carbons. So when this reacts, you first make this, which would be your primary carbocation. It reacts with the benzene, as I've shown before, to give you the minor product. Through the hydride shift, we were able to generate a secondary carbocation, which then reacts with the benzene to produce a major product. Okay, both are isomers. Okay, the minor and the major product, if you count the number of carbon and hydrogen, they're exactly the same. They're just isomers of each other, right? Because secondary carbocation is more stable than a primary carbocation, the product that comes out of a secondary carbocation is also more stable, right? I do want to take the time to relate, your idea of carbocations from the previous sequence to the material that we're learning now. So it seemed to make sense to you as to why we learn things the way we learn. All right. So stay tuned for the next set of videos where I will be talking to you about the effect of substituents. Right. Stay tuned.